First of all, thank you for having me. As already said, I'm talking about Google Container Engine today. But first of all, a little bit about PhraseApp. PhraseApp, for those of you who don't know us yet, here? Okay. We are a service which helps you with localization in your software process. That means if you're a developer and you want to work on a website or an Android app or an iOS app, and you want to provide it to as many languages as possible, then you can basically use our service, and the developer itself just needs to push the local files through to our API. Then the translators can work on the API, and when the new keys for new screens, etc., when they are translated, then you get a status report and a notification, and then the developer just needs to pull them back from the API. And then you can basically do the deployment, and the developer doesn't have to deal with merging YAML files and putting like Excel into YAML or whatever your format is. So make sure to check it out if you have the need for such a use case, or talk to me after the talk. So PhraseApp is a Ruby on Rails application, and we are around for around about 5 years now. So it's the same code base since 2012, still monolithic, so no fancy microservices involved, etc. And as we use Ruby, which is an interpreted languages, and most of you probably know the difference between interpreted and compiled languages, we don't have a compiler, which means we rely on our test suite and our CI suite. And for that we have a bit more than 14,000 tests currently, which make sure that we don't break anything when we do changes, etc. And this is where the problem starts, because if we would run these tests on a single CPU, that would mean they take about 1.5 hours or so to run, which is really, really slow, which could be optimized by writing better tests or something like that, but this is no time we want to invest in, basically, because tests get slower and slower over time, and so we wanted to tackle that from another perspective. So, running our tests. Regarding our workflow, we use a typical GitHub pull request workflow. That means we have feature branches, we push to GitHub, and we also build all the pull requests and all the branches which get pushed. And if I just wanted to update a single text on our website, or fix a small bug, that would mean in that case that I need to push it to a branch and then open a pull request, wait 1.5 hours for the build to be done, and then merge it back into master and wait for another 1.5 hours. And this is obviously no workflow we want to work with, because we want to deploy as often as possible, so sometimes 5 times a day or something like that. And with that, the day would be quite long, I assume. So from the beginning, we used a package called parallel test, which is basically giving you the option to run your tests in parallel on one single machine. And what it does, it basically partitions the tests and then uses all the cores available in your machine, and then runs for example, if you have a quad-core machine, it would probably use like 6 processors, or sometimes you can have more because of I/O heavy stuff. And they would run in parallel on your machine, and everything's quite nice. But there is an issue with that, and so our basic idea was to solve this problem with a Kiwi. So that means kill it with iron. Just have a beefy machine which is running our tests. And that's what we did, basically. We had a couple of servers at Hetzner, like 100 euros, and you got like a 6-core, 12-thread server, and that was quite nice. We could run like 12 or 14 like of these threads in parallel for testing. But yeah, there were some other issues. Another thing we do in our testing is we are kind of integration heavy. So we are not big fans of stubbing and mocking. So whenever we talk to the database, normally the case is that we go to the database. And that means if we do a specific request test, for example, we also use Elasticsearch for some bit. That means, first of all, we need to create some fixtures in the database, and then index them into Elasticsearch, and then we would go through the request, and you would need to do the database query and the Elasticsearch query, which makes the tests a little bit slower. And another issue with these dependencies is they basically have to be there all the time when you run your tests. And before we just provisioned them with something like Chef or Ansible on the machines, and we had Elasticsearch running and MySQL running, but there was obviously a better solution for that, so we started putting these in containers quite early. So we use Docker containers for all of our infrastructure components because the key aspect of that was that we wanted to have Elasticsearch in a very specific version in our continuous integration suite, because there are changes between major versions, and you don't want to run a different version than what you actually have in production. And Docker was the simplest way. You just had you just use a Docker image with a specific version, and you can guarantee that it's the same version all the time. But to orchestrate all these dependencies, and as I said, we have 3: MySQL, Redis, and Elasticsearch. We use Docker Compose. And so what is Docker Compose? Most of you are probably familiar with it. It's just the declarative way of managing your infrastructure dependencies. So you have like one big Docker Compose file where you say, okay, this is the database, this is Redis, this is Elasticsearch. And then you would run Docker Compose, and Docker Compose would spin up all the containers you need. And another benefit of that is that Docker Compose uses separate network interfaces for these containers in your stack, so you could actually run 2 things at a time without the infrastructure components touching each other. And so these managed services are basically isolated, which was also quite nice for us. So our basic approach was something like this. So this is just like some example of how our build script would look like. So first of all, we would spin up Docker Compose in the background, and we wait for the components. This is what I left out. And then we get the ports of MySQL, Redis, and Elasticsearch, and then we provide this information to the container, basically. And these ports you then get are the host ports, which are mapped from the container to the host machine where the tests are running. And we still use something like that for like day-to-day work on the development environment. And then you run the tests, and they would pick up like all these dependencies from the environment. A big problem, though, is that with parallel tests, there is this environment variable called test_env_number. And what that does is it basically gives you the option to figure out in which of these threads or processes you are running, which is important because you don't want your tests to interfere with each other if they run in parallel. So from database, that means you have 12 logical databases on your MySQL. Parallel test takes care of that, and they create that because you don't want one test to like flush or truncate a table and the other one just wrote into the table and the test broke because there is no records anymore in the table or something like that. But this is also important for writing into the file system. So you want to write into specific folders. The best way is to use a temp directory which you get from the system. And with Elasticsearch, for example, we use the test_env_number in our index names, so they don't interfere on the Elasticsearch level as well. And Redis, the test_env_number is just the Redis database, basically. So these are all separated, but you would still need that. But it's a bad thing because that means you basically have in your application code references to how you test your application code, and specifically to that one gem. So you have test_env_number on some specific bits in your code, which I don't like much, and we were quite happy when we could get that away. The other option is, as I said, the scaling out with Iron. So the affordable options at Hetzner were like, for us, 100 euros per server, and you got like 12 threads. But the slower your tests get, you cannot scale vertically anymore. So there are no bigger servers, so we got more of them, but that only meant we could run more tests, like builds in parallel. That means when like 3 developers push, they would be like occupying 3 servers, and then if the masters are also pushing, the next push would need to wait for one of these builds to pass. We used Jenkins, and we still use Jenkins. So these 4 servers at Hetzner were just Jenkins agents, and they were just waiting for new workloads. But that means also that all these jobs had to wait for the slowest test to finish, and before that, they wouldn't start a new test because we didn't want to mix up different builds on these machines. And yeah, and this is what didn't scale. And so we looked around and tried to figure out how we could horizontally scale our tests. And the good thing is that the tool we were already using provided us with an option to basically use the same partitioning. You had to be parallel execution on a physical node, but you can say, please partition my tests in that case, 128 groups, and only run group 1. And that means if you have an option to distribute your tests on a set of nodes, you could run these tests in parallel, and you're not limited to the physical cores in one single machine. Yeah, and as we were using Kubernetes already, so this was our go-to approach. So because with Kubernetes we thought we could implement such a thing. Yeah, we're running Kubernetes since the beginning of 2017 in production, and had quite a lot of experience in handling that, and so implementing that workflow was quite easy. So I don't think that there are many Kubernetes talks today. I think there is another one right after that. So for those of you who are not familiar with Kubernetes, this is just the 2-minute introduction, I would say. To me, Kubernetes is, first of all, an API, and an API which sits on the top of resources, that is, nodes in a cluster. And I have workloads, in that case that's our pods, and then you throw these pods on the API, and the API or Kubernetes makes sure that this workload is then scheduled on your nodes in the cluster, and you can scale up the cluster, you can scale it down, etc. So you have all these options. You don't have to care where things are running. Okay, so but that's the only thing I will probably mention about Kubernetes itself. And then there is pod, and a pod is similar to what Docker Compose configures. Basically, it's a set of containers. Most of the time, if you run Kubernetes, you only run one container, but kind of multiple containers. And for our testing infrastructure, that's exactly what we needed, because we would want to have the MySQL database, the Redis, and the Elasticsearch on the same node and isolated for the one test group. So that's good. And another thing is, similar to Docker Compose, these pods also have a dedicated network interface. So they are all bound to one network interface, and they don't interfere with other pods running on the same node, which is nice because with that you don't even need that port mapping thing, because you can just run MySQL on 3306, for example, and then the build pod can then just talk to the local interface on port 3306, and it knows exactly where the database is. So it's hard-coded. And the last thing about pods is that all the containers can have health checks, and that means you can see from the outside, so from the API, if your dependencies are healthy or not, basically. So you need to wait for MySQL to boot up and Elasticsearch to boot up, and from the outside you can actually see when are they healthy, when can I do something with the pod. And this will be important when I show how we actually run the thing. So the next question was, how do we deploy Kubernetes? And the first idea we had was to just use these bare metal servers, 4 of them at Hetzner, and just use kubeadm, which is the most convenient way to deploy Kubernetes on bare metal these days, I would say. But that would lead us to more problems involving especially firewall rules, for example. When you run Docker on Hetzner, it's really hard, and now they have a physical firewall, but Docker messes around with IP tables all the time, so you don't want your kubelets exposable to the world, for example. And also the maintenance was way too much overhead for us just for build cluster, because the other option would be to just go for Travis. I will be talking about why we're not using Travis or something like that later. So we said no, running it ourselves. We already run our production cluster. We're not bound to anything. We can be stateless. So the choice was to check out Google Container Engine for it, but basically only to play with it and figure out if it's actually working. Because initially we had issues regarding the pricing. We thought it was too expensive. But I will talk about that later as well. So, Google Container Engine. What is Google Container Engine? Fully managed Kubernetes cluster by the company who initially created Kubernetes, so they know what they're doing. So they basically run your Kubernetes master and all the cluster, all the nodes, etc. And you can just use the management console and say, okay, I need a new cluster with that amount of nodes. It's zero ops, so you don't have to take look at anything. Like they even do like fixing of broken nodes, etc. So it's really, really convenient. And they also provide you with a well-defined upgrade flow, which is always hard when you want to upgrade your own Kubernetes cluster. It's getting easier and easier with all the new versions of kubeadm. But in Google Container Engine, it's basically just an API call, please upgrade my cluster. You don't have to care about that as well. And the last bit is AutoScaling, and that's basically where we, that was basically the feature we found which stuck us with Google Container Engine. So, with Container Engine, you have node pools, and that is just a subset of nodes which all share the same configuration. So it's similar to what AutoScaling groups are in AWS, and I think in GCE there is node sets or something like that, placement groups, whatever. So they all have a specific image type, so you can specify that you want to run like the Google container image, or I think you can also run Debian or something like that, but normally you don't fiddle with that. A machine type, that means how many cores do you want in your node pool, and then a number of nodes you want to have running in that pool, and also for auto-scaling, you can configure how many you want to have minimum and maximum. So these are like the boundaries in which the node pool can scale. And what you also get with Google Container Engine is the Google Container Registry, which is a set of fully managed private Docker registry, which you can access from the cluster, but also from your local dev machine. And it's basically almost free. The only thing you pay for is the storage capacity you're actually using, and it has no limit. So you can. It's just, I think, a layer on top of Google Cloud Storage, and so there are no limitations. We run the ECR alternative on AWS, and there you have like a maximum number of images, 500 or something like that. So you don't have any of these issues there, and it's really, really fast from inside the Google network. And to have a Google Container Registry for our build process is really important for us, because our flow is always to build a Docker image of our application, bundle all the dependencies, etc., and then we need to distribute that to the pods which are actually executing our tests. Yeah, and in combination with service accounts, these are like features you enable in your node pool, and you can allow your nodes in the cluster to push into the registry without any credentials, etc., which is working really, really nice. So, yeah, and the critical bit now for the pricing, and this is like the auto-scaling, but also the preemptible instances, was the reason why we found that Google Container Engine is actually much cheaper than what we paid before at Hetzner, because there is an option of using preemptible instances, which get like an 80% discount, so you only pay 20% of what you normally pay for these instances, but they come with two drawbacks. First of all, they can be terminated any minute, so you have like one minute warning to like complete your stuff. And the other thing is that they have a runtime of maximum 24 hours. After that, they are terminated anyway. But for running our tests, that's perfectly fine, because normally our tests should finish within 1 minute or something like that. Not really, maybe 2 or 3 minutes or something like that now, or like these partitions of tests. And even though if the tests fail, we just restart the tests and then wait for a new node, basically. And it doesn't happen that often, but it's really, really cheap. So when you look at the prices, and this is like the core metric for us is cores or threads per day in euros. So in AWS, it's round about €1 per day per core, basically. So when you run an instance the full month, it would be like 30 euros a month, something like that, single core instance. You can have like reserved instance, etc., so you get a discount of maybe 30%, a little bit more, but this is the ballpark number. On GCE, they're always a little bit cheaper, I think, than AWS. And also the discounts are more transparent because you get them automatically, basically. But you are the default is to have 97 cents. And you would get like 30% discount if the instance would run the whole month. So with HeadSnap, you see like this is the pricing gap. I just calculated the number of threads we had and broke that down to around about 25 cents. And with these preemptible instances, we are at 20 cents. But there is a little star involved here. So the threads you get at your own, like say on HeadSnap instance, are around about 20% faster than what you get like the virtual core on Google Cloud. But when you do the calculation, you are at the very same price point as you are with HeadSnap, basically. That is cores, bang for the buck, basically. But that in combination with the AutoScaling makes things much, much cheaper then. Because with AutoScaling, you get horizontally scaling of your node pools basically for free without any maintenance. And how that is implemented or working is, as Google is already running your API for you, you basically just place a workload, a pod on the cluster, and you say, please run on a specific node pool. And whenever there is no node in that pool, these pods would stay in a pending state because Kubernetes cannot like schedule them on any node. And when you have a certain number of pending nodes, then the autoscaling automatically kicks in because the autoscaling then can figure out, okay, what do I need to do that your workload can run? And that is most of the time scale up the node pool. And that's triggered completely automatic, so you don't have to do anything. And whenever your pod's finished, you terminate them. There is a grace period, and after that, the nodes are scaled down again. That means our build nodes are not running on the weekend. They're not running like at night, etc. So it's basically our like the 10 hours we are pushing. Whenever we don't push, no node is running, or at least no worker nodes. There are still like some nodes which are always running, which are like the endpoints for the GitHub pushes, etc. But yeah, that's basically it. So how does the execution look like? So first of all, we always create that Docker image. We then use to run our tests. We then push the Docker image to the Google registry. And after that, we create, and in our case, it's 64. That's just how many we want to run in parallel. Build pods. And these pods have all the dependencies configured, as I said. And then we have a process which is waiting for health checks to be successful. And after that, we know like the pod is basically running, and we can run our tests on the pod, and then we use a tool, kubectl-exec, which is just the command line execution, which is similar to what Docker exec does. So you go into a running container or a running pod, and then you execute your tests, basically. And with that, you get like, first of all, you get the log output, and you also get like the exit code of the process. And then we just need to collect these results of these kubectl-exec commands. So this is all running in parallel. Then we terminate the build pod so that the capacity on the node can be used by another build, basically. So our build container, normally, like we started with just a sleep infinity, basically. But this is a little bit more fancy, I would say. So what we do in our build container is we create a file descriptor, a FIFO, where we just cut the output from. So basically everything which is written to that FIFO is then also like printed out in that build container. And the reason behind that is that with Kubernetes you get the feature that you can attach to the logs of running pods, basically. And when you do kubectl-exec, you don't get these logs from the API. You only get them when you run that. But what we do then with kubectl-exec is that we pipe the output to this file descriptor, so we can conserve the output logs of our build, basically. And that can be indexed by LStack, etc. So we have that information all the time, which is really nice. And then the infrastructure containers, this is similar to how the Docker Compose configuration is probably. In that case, it's our Elasticsearch configuration, so we run a really old version of Elasticsearch still, so we rely on having a specific version, but we are on the path to updating that. For Elasticsearch, an interesting bit is that we actually ran into interference issues with our approach when we didn't enable the node local thing, because these Elasticsearch nodes would then form a ad hoc cluster on Google, because like the container network was supporting broadcasting and stuff like that, and so you had like issues with your testing. So we put that in, and things fine. And then this is basically as simple as the health check is. Say that there needs to be some HTTP available at port 9200. MySQL is just a MySQL command. And then we have the test execution. So this, like the infrastructure and the other, the build pod are part of the pod manifest. And then the test execution is basically this. Go to the created pod when it's available, then run these parallel tests. In that case, it's group 1 of 128. And then pipe that to the temp console thing and wait for it to return, basically. And for that, we'd like to do a brief demo, and I'm hoping that things work somehow. Let me see. So, I need to speak a little bit louder, probably. Is that visible? So we have some, like here in the bottom you see that are currently no pods running in our cluster. We can here watch the nodes maybe. Let's see. Yeah, sure. Thank you. A little bit smaller. Hope that's still visible. So currently in our cluster there are two nodes which are basically for our cluster services. So you need some nodes in your cluster running, and we have one bigger node for our Jenkins, and these are the nodes which are always running. We don't terminate these. And when I want to run our tests, I can just say wrong directory. So first of all, I created a new namespace, and that's just to keep the pods which are running in that very namespace isolated. And the good thing about, I think I can not use it. Thank you. I might get back to you soon. So a new namespace, so all the pods in the build, which you can see at the bottom. So they are all in the pending state. These are the 64 pods we are currently running. And so they are basically waiting for a node to be available. Kubernetes is waiting for them. So this takes a little bit of time, and they are running in a namespace, because the nice thing is when you want to clean up, you just destroy the namespace, and then all the pods are also destroyed, all the resources which are executed there. And maybe I can look into how the pod itself looks like. So the runner is a Go script. Which is getting a normal YAML. So this is how a resource on Kubernetes looks like. And we have some template placeholders, for example, the name and the namespace we want to put in from the outside, and especially the image, because the image is created before, and I'm using a pre-configured image. And yeah, so this is then rendered into it. And then we have, for our build pod, we have limits. That means the build pod should have at least 0.75 CPU cores and at most 1 CPU core, so the scheduling works better. And everything is running single-threadedly here then, so there is no parallel execution here. So this is the environment, for example, the database URL, Elasticsearch URL, Redis URL. Then you see, for example, this is the database configuration, Elasticsearch configuration, and the Redis configuration. Yeah, you see that there are nodes being spawned by Google, so a few of them are already running, so these are, I think, 8 nodes now, because each of these nodes has 8 CPUs, and if I have like 64 pods, I need 8 nodes. Okay, so let's see. Now you see that the pods here are being in the container creating state, and that just means that the image which I just created from the GCR registry needs to be pulled down, because these nodes are all brand new, so they don't have any state yet. So this is the latency, which probably takes us like, I don't know, these one are running already since 2 minutes or something like that, so we can give it another try, maybe 2 more minutes or something like that. Then these should be running, and then the first test should like terminate within 100 seconds or something like that. We can just keep that running, and maybe I can do like a quick QA already. So are there already questions? None? Should I show something like any more detail towards like the pod YAML or something like that? Nothing.
Can you show the script where you start all the segmented tests?
Okay, the Go script. And this is just a demo. Like we use a different script. It's, I don't know. Let me see. Nope. Wanted to figure out how many lines these are. 500 lines of Go. It's probably too complicated to explain, but it's just shelling out to kubectl create here, for example. And then you have some. There is an API where you get updates to pods, and that means when a pod gets healthy, then you get basically a JSON message that the pod is healthy, and then I can start the running of the test basically. So here you see, for example, that these pods are now running. So these took 4 minutes or something like that to be available, and that was the cluster is completely cold. And then we can also like attach one of these pods, hopefully. Let's look at this one here. So first of all, I need to provide the namespace. Yeah, and there are multiple containers, so I need to provide the container, and you see these are our deprecation warnings of the test. So I can look into what is currently happening in these tests, and then maybe I wait for some to finish. And I mean, this latency is normally only visible when there didn't happen a push within like 15 minutes. It's also one of the most painful things in our setup is that whenever we don't push for 50 minutes, we have that latency. So our setup basically encourages us to push more often, because then the tests are faster. But I'm hoping for Google to provide an option to increase that grace period. So for us, for example, we could live with a grace period of 8 hours or something like that, because these nodes are really, really cheap, maybe an hour or something. So now you see that the first test passed. So these are green. So the test group took 100 seconds, and they're also not evenly distributed. So the slowest test group takes a little bit more than 200 seconds. But you should see more and more tests getting green. So the one I currently attached just got green, and then you see this is getting much faster. So you see you would already get like an instant feedback if some of the group broke. So you could already look into what the problem was right after that. And if I started another run of that thing here. So this would be much faster now, because there would be like it takes like 11 seconds for a warm cluster to get workloads, and then you see that here that I can then run multiple builds in parallel, and here you see it took 15 seconds for these pods to be available compared to 220 seconds or something like that. and you add 100 seconds to that, and this is your test suite. And whenever we push often, then these builds probably take us 5 to 7 minutes or something like that. Okay, so yeah, I'll just leave that running. So go back to the slides. So in summary, yeah, we can now actually fully autoscale our CI cluster. We currently run our the worker node pool with what is it, 32 at maximum. So whenever we have, so that means 256 processes in parallel, but there's no point in not going towards 64 or something like that, depending on how much we push. We don't have that many developers. We are only like 6 to 10 developers most of the time. But this should also work for much, much larger teams because you can scale these clusters up quite good. And I wanted to mention like the comparison to what we would pay with Travis, for example. I think the biggest plan with Travis to have 16 workers in parallel would be around about 500 euros or something like that. And this setup costs us like 300 euros, but we have the capacity of 128 compared to 16, which is really nice for us. Our tests are now as fast as our slowest group, basically. And it's just a matter of improving like a specific test file, the performance to improve the whole build quite drastically. And the configuration is basically you can decide how much you want to pay for your tests to run, and you don't have to scale anything manually. You just update the node pools, and it's just a matter of how much you want to spend for your tests, basically. A little bit of Outlook. So we still run that in Jenkins with a similar script to what I showed. There are options to have Kubernetes plugins for Jenkins. We didn't look into them just yet. They can probably give us such an experience as well. With that option, I can also run them locally, basically. I can trigger the builds without any pushing. So I just need to build a new image, push it to the registry, and then run the build and have instant feedback if I broke something. Another thing we might be looking into is Google Container Builder, which gives us a fully managed way to build container images. We're not using that. And the third one is to have something to keep alive of the nodes. So the 50 minutes grace period is actually really, really short for us. So the idea is to have some service in the cluster running, which figures out that there is a new node up, and then starts a pod which just sleeps for an hour or something like that, which means that a node would not be terminated within 1 hour, and so we could improve that. So that was it from my side. We're always looking for developers, so in case you're looking for something in the Rails jobs, or we also provide Go, feel free to talk to me afterwards, and thank you. Are there any more questions now? Yeah.
In the total spectrum, what is the time that you reduced from the 81 minutes before and current time is?
Our builds are currently including building the image, basically. This takes some time, and we have a lot of gems, and the caching is now working perfectly to just under 10 minutes or something like that for each branch. So it would still take us 20 minutes, but it's something we can live with, basically, with 2 builds. And we could also figure out that to merge the master already into the pull request and run that in parallel or something, so we could reduce that. But it's 10 minutes is basically the time. When our tests get slower than 10 minutes, then we look into how we can improve them. And that's been the case for the last 5 years or so. More questions? Good.
Okay.
Yeah, thank you. Then I'm going back to my
Hackathon.